Jnanam paramam dhyeyam. Knowledge is supreme.
Just to recap, what is wave function, which you have already seen, I put it as a plot here. The mod of the complex wave function, mod squared of it, it's going to be positive definite, and there is a plot as a function of x. And looking at the plot, you can try and define formally probability of finding a particle between x and x plus dx at a specific time t will be mod of psi of xt mod squared dx. It's nothing but it is this area which is shown here. I put a shaded area here, and that gives you the probability of finding the particle between x and x plus dx. If you want to find the probability of finding the particle between x1 and x2, what do you have to do? You have to integrate between x1 and x2, and that will give you the shaded area under this curve. So, the probability of finding in the region x1 and x2, that's going to be the mod psi squared integrated between x1 and x2. Okay, so that will be the total area shaded under this curve. So, one is to have some kind of a pictorial view, not to mechanically do integrations, differentiation, but you should also know that both the math part as well as the graphical part and experimental data, all these things should be in your mind when you understand quantum mechanics. Okay. This also you have kind of been imposed when you did all the potential step function, well, barrier. In no region you want your wave function to blow up, right? Did you allow anywhere the wave function to blow up? If you had an exponentially growing function, if the region goes up to infinity, plus infinity, then you put that coefficient to be 0. Okay. So, you will make sure that the probability is always a finite quantity, it is not infinite. Okay. So, P which we find for x lying between x1 and x2, this has to be integral x1 to x2 mod psi squared dx, okay, and this has to be finite. Okay, the mod squared, we will do a box normalization. We'll come back. Yeah. So, the question is that if suppose you have a wave function which is e to the I kx, okay, the claim is that when I do the probability mod psi squared, that's 1, and integral of mod psi squared dx can, if you go from minus infinity to plus infinity, it will be infinity, because this is 1, mod psi squared is 1, but what you will do is you will put it from minus L to plus L or something, okay. What will that be? It will be 2L, right. So, we will keep it as 2L and do all our observable calculations which are averages, and then this L will get cancelled. So, it is, even though it is not a, it looks like from this expression that it is infinity, you can regularize it in this way for the oscillatory function. These are called oscillatory functions. and you keep this L and later on you put L tending to infinity, and all your calculations will all be finite. Okay. So, this is one of the important requirement which is called a square integrable condition, and square integrable functions is for formal definition. If you have psi of xt, you have to make sure that it goes to 0 faster than 1 over root x as x tends to plus or minus plus infinity. If I am looking at the positive x axis, mod x tends to plus infinity, and for such functions you can normalize them, and normalization condition is that the mod psi squared dx in the entire regime, the range, it depends on the situation, but if you are looking at a region which goes from minus infinity to plus infinity, this integral has to be equal to plus 1. Most of the time your wave function may not be normalized, but you can normalize it. Like for example, if phi of xt is another wave function whose integral over the whole region is capital N, N is called as a normalization constant, and it should be finite. And how do you write the normalized wave function? You try to put 1 over square root n on the unnormalized wave function, and if you try to do mod psi squared integral, that will be normalized, and you also want your normalized wave function to go to 0 as x tends to plus or minus infinity. So, these are the formal definitions of the square integrable functions, and for you to call it as a normalizable wave function. Okay. So, this is one exercise which I want you to do. Use the time dependent Schrodinger equation which I showed. The slides will also be there. I will try to put them on Moodle also for you. Show that the rate of change of probability, this is the total probability. We have seen that the total probability is normalized, it is a constant. Use the Schrodinger equation and show that it is 0. Okay. That is the question. More exercises. Starting from expectation value of x, how do you write the expectation value of x? How do we write expectation value of x? If I assume psi to be a normalized wave function, this is the way we will write the expectation value of x, right? I'm just recalling what you have learnt in your first year course. So, you start from the expectation value of x, show that d by dt of that expectation value, we do the algebra and show that it is expectation value of momentum. Momentum, you all know, momentum expectation value is minus IH cross del by del x. So, that is the momentum expectation value. So, what does this equation tell you? Classical mechanics, when you do, right hand side, the extreme right hand side is actually velocity. Right? You can write this as mv, then it is expectation value of velocity. Expectation of velocity, please derive this, okay. So, this is an exercise. Expectation value of velocity is rate of change of expectation value of position. Classical mechanics, you did not have expectation value, but you would have done d by dt of x to give you v, okay. If you want to match with classical laws, it is the expectation value which satisfies the classical laws. Quantum ideas, momentum is minus I h cross del by del x. It does not give you any matching with classical laws. But if you want to understand classical laws, find out the expectation value and see what equation the expectation value satisfies. Okay. So, this explicitly when I do it, you see that d by dt of expectation value of x is 1 over m times expectation value of p, which is what we expect for a classical law where we do not do expectation value. Exercise 3 is also familiar to you. If you are in the presence of a potential energy, the force law will be the minus gradient, conservative potentials if you have, the force will be proportional to minus gradient V. Everybody knows that, right? Classical. But now, in quantum physics, your expectation values have to satisfy the equation. So, please verify these things using this formal definition of how one writes the expectation value, given an indication. Please verify this and we could have a discussion on the tutorial session on Monday, okay, if you are not able to prove it. But please try to do it. Okay. So, these classical laws satisfied by expectation value in quantum physics, this is comes under the title as Iron-First theorem. Expectation values obey classical laws. Okay. Okay. A couple of things which you have done in the previous course. One is when we have a particle in a box, V equal to right. This is something which you have used. And you have also done, potentials which are V minus, V plus, x equal to 0. Yes. So, these are finite. V minus and V plus are finite. Right. When you did this finite potentials, you made sure that psi minus the region at x equal to 0 should be equal to psi plus at x equal to 0. What else? d by dx of psi. So, this is psi minus evaluated at x equal to 0 should be same as on psi plus at x equal to 0. So, this is continuity of wave function, this one, and this one was continuity of derivative of wave function for finite potential. But once I do a particle in a box, which one is removed? The second one is removed. Why? Do you know the reason? So, suppose you make it infinite, then you expect that That's one way of seeing it. And we would like to see for other kind of potentials. What are the other kind of potentials? You all learnt about Dirac delta function in your math course? Yes. So what is that property? Suppose I have V as V naught delta of x. This is the delta, Dirac delta function. We expect what? We expect psi of x, psi minus of x to be same as psi plus of x. Continuity of wave function, there is no problem. Even for a particle in a box, your wave function should vanish at x equal to 0 and at x equal to L, and there is a continuity. Once there is infinite potential, wave function is 0 in the outside region of the box, wave function is continuous. The derivative of wave function cannot be checked for infinite potentials, right. So, the derivative of wave function in general only for finite potentials will be continuous when you go from region 1 to region 2. This is the statement we make, and as he has already pointed out, if you go and stare at the Schrodinger equation, you can actually prove these things. Okay. So, that is what I am going to show now, okay, just to take you on the tour of seeing it from. Okay. So, take V of x below x equal to 0 to be V minus and V of x to be V plus for above x equal to 0, x greater than 0. And if you take the Schrodinger equation and write the double derivative as difference between the single derivatives divided by epsilon and integrate over dx. So, d squared f by dx squared, if you want to write, how will you write this? df by dx, okay, evaluated at x plus epsilon minus df by dx x minus epsilon, then divided by 2 epsilon. Right. If you want to integrate this over dx, you can also integrate this over dx. You can remove this from. Okay. So, this will give you okay. So, let us do this. So, take that double derivative of the wave function and rewrite it as the difference between two single derivatives integrated over dx. So, that 1 over 2 epsilon cancels and you will have the other term V of x minus E. So, this is just the Schrodinger equation which is rewritten here, time independent Schrodinger. Now, you can play around putting V of x from minus epsilon to 0 plus another V of x between 0 to epsilon and substitute V minus and V plus and take the limit epsilon tending to 0 limit. Okay. We are looking close at the boundary between the two regions. Is that right? So, if you do that, there will be an epsilon factor multiplying. You also use the fact that psi of x is continuous. So, you can pull out psi of x as psi of 0 out of the integral. Psi of x is continuous, so you can pull out psi of x as psi of 0 outside the integral, and this V of x will become V plus plus V minus, okay, and you will have an epsilon because of this integral over dx. Similarly, E of psi of 0 times another epsilon comes, okay, 2 epsilon. When you take the limit epsilon tending to 0, what happens to the second term? Second term, as long as V plus and V minus are finite, epsilon into a finite quantity where epsilon tends to 0 is 0. That is why the second term will become 0. The second term becomes 0. This is what he pointed out already. You will have your first derivative of your wave function at plus epsilon and first derivative of the wave function at minus epsilon will be continuous across the boundary. It's very clear from the Schrodinger. Will you do this intermediate step? Please do this intermediate step, explicitly putting in V of x in this appropriate region. Take the psi of x out as psi of 0 because psi is continuous, and check that you get continuity of the first derivative. Please check it. For infinite potential, suppose some region you make it infinite, okay, even if V minus is 0, you make if V plus is 0 and you make V minus to be infinity, even then there is a problem because there will be an infinity multiplying a 0, and you have to be careful when you have 0 multiplying infinities. Okay? When you have such problems with some potential, in some regions where potential becomes infinite, you can't assume the first derivative of the wave function to be continuous. So that's why the derivative of wave function is not continuous for such potentials. Is that right? So what have we said? We say that d psi by dx in region 1 at x equal to 0 should be d psi in region 2 at x equal to 0, if x equal to 0 is the interface. If V plus or V1 and V2 are finite. If V1 is infinity, V2 is finite, then we don't have this. So the immediate problem which we can try to solve is V equal to V naught delta of x. Okay. So how do we do this? We will have a h cross squared over 2m d psi by dx at epsilon, right, minus epsilon. Let's center it around x equal to 0, minus d psi by dx at plus epsilon, or is the other way around, plus epsilon, and this one will be minus epsilon, plus integral v of x minus e psi of x dx from minus epsilon to plus epsilon. Is that right? And we are going to substitute for v as v naught is a constant and delta of x. So let's substitute that. V of x psi of x dx will be what is this? V naught psi 0 minus epsilon to plus epsilon, e psi of x dx is e psi of 0 dx, and in the limit You have to take limit epsilon tending to 0. That will be, that's going to be, so this term is 0. V of x psi of x is V naught times psi of 0, which is finite. So in the context of delta function potentials, we can try and tell minus h cross squared over 2m d psi by dx at x equal to minus epsilon minus d psi by dx at x equal to plus epsilon, or the other way around. So you can remove the minus sign and make it plus sign here. Okay, will be plus V naught psi naught equal to 0. So what have we achieved? In the context of particle in a box, we cannot find the amount of discontinuity, right? We did not even worry about it. Here, even though it's an infinite Dirac delta function potential, I can tell the difference, what should be the discontinuity element to go from the x minus region to x plus region by this specific, if you know the wave function at 0 and V naught is the factor multiplying the delta function potential, I know exactly the amount by which there is a discontinuity in the derivative of the wave function. Suppose I give V to be V naught delta of x plus a plus delta of x minus a. These are the double delta functions. So these are the various potentials where you need to get a feel of what is the solution and when can you get bound states. You know what is the condition for a bound state? Why do you call it as a bound state? Particle, harmonic oscillator, what is the requirement? Is it a bound state? Do you know? When is a scattering state you can get? All the free particles are scattering, right? So there are two regimes. If energy of the particle is greater than V, you have the scattering states possible, you have the states which are transmitted. And there is another regime which is energy of the particle less than V. Okay. So these are the two regimes which you might have. This is what you would call it as a condition for getting bound states. Right. So now what we would like to do is, let's formally, in the next lecture, let's formally put in the conditions for the bound states, which is how the way we should look at bound states. And then we could try and do some of these delta function for potential, double delta function. When will it be a bound state? When will it be a scattering state? That will depend on the sign of V naught. Okay. So these are things which we will start exploring purely from the wave function formalism. For it is just a 1 week, we will have a warm up doing these things and we will reproduce all these things from the linear vector space notation. So that's the idea. So you need to know these things. You cannot say I will forget this. You need to know the wave function formalism. You should also know how these can be reproduced from the Dirac notation of the vector space and Dirac bracket notation. Okay. So I'll stop here.